pyrometers, so that those are equivalent to bolometers in infrared detectors that will detect temperature, high temperature, through radiation of the infrared spectrum. So usually this goes in a bundle of wires. I have optical fibers. If I talk about high temperature, this optical fiber is sapphire, a fiber that would stand withstand 900, 1100 degrees. The support also same temperature, and again we have a sensor, infrared sensor detector for the temperature, and also converter from optical to electric, because again FADEC has no optical interface. Right?
So is it's just the window that's sapphire, or the cable, the optical fiber is also
optical fiber is here. You have the bunch of optical fiber,
right,
and in here you have the sensor and the converter.
So the entire fiber run is about sapphire.
Right, exactly. It's fiber because I have to go to the
right, but it's sapphire.
Sapphire, yeah. It's a bunch of sapphire wire. Right.
And you have typically you have a lens on top of it, because you want to measure at a certain spot that's away.
Right.
The sensor is.
You want to take the sensor out from 1,000 degrees.
It looks by some hole to the rear part of the HP turbine plates. In case of this, and there is purge airflow into the hole to keep the lens clean.
Yeah, and that is another issue.
So this is the T41 you mentioned.
That we would be happy if it's actually something like T43.
More like T43.
We measure something exit of HP.
The first stage, okay. Exit on the first stage.
Yes.
Okay.
We're looking at the rear part of the HP turbine.
Because they speak a little bit of Chinese, I'll translate for you. You recall the graph Sanjay had with the sections of temperature and pressure, and it's a section from 11 to 90, I think, right?
Yeah, 8 and 9, yeah.
8 and 9. And then, I mean, when you talk 43 or 42, it's the section in which they take the measurement.
T41 is the turbine inlet blade temperature. Yeah. So that's the first stage that after
41
the
is actually.
So 42 would be the rotation, and 43 would be the next stator.
Yeah.
So it's the second stator after the first
somewhere
stator.
upstream of 43.
Yeah, okay.
Now, pressure measurement.
T41 is the important one for control, and so you measure T43 and you use some kind of prediction as to what T41
Use some correlation to.
Let me finish.
Sorry.
So basically pressure, it includes lots of measurement of pressure. We talk about oil, gas pad, fuel, bleed air, all kinds of pressure. So these sensors would be different. But in principle, any pressure sensor, it's more or less same. We have a sensing element that is restoring element of membrane that would be deflecting, and based on that we figure out what the pressure is. Now, it is also...
Sorry, I had a question.
Sure.
You mentioned vibrating air cylinder. Is that usually the...
I know in burners, they use, in the static burners, they use that method to measure both temperature and pressure with resonant tubes. There are also a few patents on that. So there's a method indeed. It's very advantageous because basically what you have to do is acoustic measurement. And if the burner is not too noisy, you could perform that.
So instead of a deflection-based measurement, you have a frequency-based measurement.
Right, exactly. That goes in acoustic domain, and you could basically record it. Definitely there are sensors that are dedicated, for an example, integrated temperature and pressure, that are basically used for the creating ice and pouring object. They are protected against those, and they operate for the fighter, for the military engines, right? So one has temperature and pressure integrated in one single unit, right? But they are dedicated for a platform. You can't buy the shelf and say, okay, I'll use it for me because it might not fit, right? So this is another aspect in here. Other pressure measurements, we have few types of detection, or I should say the materials used for measurement, and they are either piezoresistive silicon on silicon or silicon on sapphire. Silicon sapphire will face a little bit higher temperature, but again, this is only the transducer. We talk the electronics, we have the same limitation. Silicon starts diffusing at 250 degrees. We don't want to reach there because it's already diffused. In half an hour, you lose the circuit. So it have to be up to 200 or even lower than that. That's why the specification is this low.
Can you clarify the difference? Silicon and silicon is the transducer is also silicon, the electronics is silicon.
Silicon and silicon. Whereas silicon on sapphire is the membrane, silicon is the electronics.
Sapphire is the membrane.
Right. So if you have, for example, that sensor has to face an environment that it's, you have a flame, but it's not more than 200 degrees, then you have from time to time flame, or you have some debris or something. Sapphire will face better than silicon the harsh environment, right? Piezoelectric pressure sensor. This is sketch from vibrometer. This is a piezoelectric with a natural crystal. You know the product, and it's a little bit bulky for the application, but it's used for outlet pressure. Differential pressure switches, they are also pressure sensors, but they switch when I have specific differential pressure that will open a valve, or they are very much used in this control on-off valve opening and bypasses or oil lubrication, for example. We have sensors like that.
So are the piezoelectric sensors, the vibrometer type sensors, the ones that are used generally in aircraft engines?
Right. They are used, and probably their sensors are used as well. Okay.
No, they use a different piezo material now. It's gallium phosphide. Yes. Because it's stable up to 900 degrees, and you can typically measure up to 560 degrees. That's the limit of the best material.
Now,
you're getting close to 5 o'clock, so what's your plan?
I have to finish this talk because tomorrow I have another one that is also lengthy.
How long would you-
Because you interrupt me too much.
I only did once.
No, I'm just kidding. Okay, so it's good to have interest on that, right?
Yeah.
It's 5 o'clock. There are a few minutes. I'll finish in probably 10 minutes. Give me that time, please.
So everybody's okay with that?
Yeah.
All right, very good.
So what happens in here in speed and 1 per revolution, usually these are magnetic sensor or radio frequency sensors that will detect position of the blade. Now, for an example, we talk 1 per revolution. We expect that if we detect the position of the blade in a normal condition of the regime, we'll get a spike or a sinusoidal response. But if at one point we have an expanded sinusoidal loop, that means the blade came later on. And this coming late could be because of dropping, because of particle insertion, whatever. So that is an indication, and sensors like that are available again for specific applications. They have the shape, they have geometry, just to fit in a platform they are designed for. They are not so much interchangeable, unfortunately. Torque sensors, they are basically mostly used for helicopter engines. What is the principle in here? I have a torque bar that is a given length, and I have this phonic hose that it's called. Basically, it's a type of gear with a spacing that it's established, it's calibrated. Now, when the shaft rotates, the relative position of this gear changes, and when they pass next to a magnetic sensor, a Hall effect sensor, that position will be detected. Same as looping the sinusoidal higher or lower, I know what the torque is according to this distance, because again the shaft is known as this. It's calibrated as strength. Now the point is that they need recalibration very often, about 6 months. Every 6 months they have to be recalibrated. Position sensors, you could have position rotation or position in longitudinal linear position. And they are standard sensors they use everywhere, and the same thing in aircraft. They have to have just a design that fits the platform. Proximity sensors, they are usually magnetic sensors, and they will detect if the actuator reaches a limit or a blade reaches a certain position which is not intended to, or so on and so forth. We need a ferromagnetic target to be traced. Right? Magneto-optical sensors, they are basically steady-state sensors with optical fiber transmission that, sure, definitely later on has to be converted to electrical signal. Basically, this sensor will detect the temperature, optical magnetic pattern through modification of the optical output of the signal. There will be a. This is very small, by the way. Very small means in the range of 1 millimeter or so. In this 1 millimeter, we have a set of green lens. These green lens are lens that enable single mode light to go through the optical fiber. They multiply, they're multiplexing the multiple mode light. And this single mode light will modify according to magnetic field. So the frequency will modify, will shift according to the magnetic intensity of the magnetic field. So this is basically used to detect proximity and modification in the magnetic field in general. Displacement sensors, we just discussed about position. Displacement is more or less same. It's an LVDT or inductive. Fuel flow, basically the true mass fuel flow meter. It's used for hydraulic drivers. Also has to be used somehow for fuel. You know, fuel has to go into the engine that is heated up. When we don't need, the fuel comes back, but this has to be cooled down. So it's this point in here, this type of technology for measurement of fluid flow of fuel or of liquid, it's still in a crude shape because the accuracy of this measurement has to be significantly high. It's not on centimeter cube per second or so. It has to be much less than that. Vibration transducers, these are inertial sensors, but as you see here, they are packaged for the application. The holes are positioned such that they fit exactly the application. Connectors are fit with the application. So range of measurement, we could go from 0.2 G, that would be the maximum range, to 2000 G at this stage with this integrated circuit devices. Temperature limitation, same thing, 150, 100, 200 degrees tops, because the electronics is included in. Light off detector. This is used to detect when the flaming burner is off for whatever reason, blow off of the engine when we have too little fuel. And these are basically UV type of sensors. It's a big hit in UV development, UV sensors development in early 2000. There are lots of sensors on the market, but they are not needed. People thought at the time there would be a market for them, but apparently was no market on that.